Evapotranspiration is the process by which water in the land surface, soil, and vegetation is converted into vapor state and returned to the atmosphere. Evapotranspiration refers to the combined effects of evaporation and transpiration from an ecosystem. Transpiration is the process by which plants transfer water from the root zone to the leaf. Osmotic pressures at the root level act to move water into the plants. Water is transported through the plant's stem to the proximity of the leaf surface. Air enters the leaf surface through small openings called stoma or stomata. Chloroplasts within the leaves use carbon dioxide from the air and small amounts of the available water to manufacture biomass, that is, glucose, releasing oxygen as a byproduct. Water escapes through the stomata as air enters and is available for evaporation. The ratio of water evapotranspired to that used in biomass production is very large, about 800 or more. Transpiration occurs continuously, but it is limited by the rate at which moisture becomes available to plants. Transpiration rates are a function of the same meteorological and climatic factors that determine evaporation rates. Evapotranspiration includes all the water returned to the atmosphere from an ecosystem. Potential evapotranspiration is the amount that would take place under the assumption of an ample supply of moisture at all times. Potential evapotranspiration is an indication of optimum crop water requirements. Reference crop evapotranspiration is the evapotranspiration rate from an extended surface of 8 to 15 millimeter tall green grass cover of uniform height, actively growing, completely shading the ground, and not short of water. Potential evapotranspiration is equivalent to the evaporation of a body of water with negligible heat storage capacity. The methods to calculate evaporation and evapotranspiration overlap one another. The Penman method is used for both evaporation and evapotranspiration with appropriate coefficients. Evapotranspiration models are of several types: temperature models, radiation models, combination models, pan evaporation models. The Bellini Cradle formula is typical of the temperature models to estimate evapotranspiration. The formula has been widely used to estimate crop water requirements. Its original form in U.S. customary units, applicable on a monthly basis, is in which F equal evapotranspiration in inches per month, P equal ratio of total daytime hours for a given month to the total daytime hours in a year, T equal temperature in degrees Fahrenheit. The average monthly value of the ratio P is 1/12, that is 0.0833. In SI units, the Bellini Cradle equation, applicable on a daily basis, is in which F equal consumptive use factor in millimeters per day, P equal ratio of mean daily daytime hours for a given month to total daytime hours in the year in percentage, a function of latitude, T equal mean daily temperature in degrees Celsius. The average daily value of P, applicable along the equator, is P equal 100 times 0.08333 divided by 30 equal 0.27778. The consumptive water requirement is equal to the product of the consumptive use factor F times an empirical crop coefficient K sub C, which varies as shown in the following table. Bose and Pruitt had proposed a modification of the Bellini Cradle formula, which has been widely accepted. In which Et sub is the reference crop evapotranspiration, and A and B are constants that vary with actual insolation time, that is, the ratio N/N between actual and maximum possible bright sunshine hours, either low, medium, or high. Minimum relative humidity, either low, medium, or high, in percentage, and daytime wind speed, either light, moderate, or strong, in meters per second. Values of A and B for the case of moderate daytime wind speed are given in the following table. The consumptive water requirement Et sub C is the Thornweight method is also used to estimate potential evapotranspiration. The method is popular because it is based only on temperature, which is widely available. The method is based on an annual temperature efficiency index J, defined as the sum of 12 monthly values of heat index I. Each monthly index I is a function of mean monthly temperature T in degrees Celsius. Potential evapotranspiration at 0 latitude in centimeters per month is calculated by the following formula. At latitudes other than 0, potential evapotranspiration is calculated by the following formula. K is a constant for each month of the year, varying as a function of latitude. Priestley and Taylor proposed that potential evapotranspiration be taken as the radiation part of the Penman equation multiplied by an empirical constant. Defining alpha equal delta over gamma, the Priestley-Taylor equation simplifies to the relation between evaporative heat and evaporation rate is in which rho is the density of water and lambda is the heat of vaporization. Thus, the Priestley-Taylor equation is constant 1.26 may vary with climatic conditions. It has been reported to be 1.7 in arid regions. The original Penman model provided an estimate of evaporation from a free surface. Experimental crop coefficients were used to convert evaporation to evapotranspiration. These coefficients, 0.6 in the winter and 0.8 in the summer, were intended to multiply the evaporation to get the evapotranspiration. Other studies have suggested that free water surface evaporation and evapotranspiration are nearly the same. energy budget, and mass transfer components may compensate themselves to make evaporation and evapotranspiration nearly equal. Pan evaporation models are also used in evapotranspiration studies. The most common evaporation pan is the NWS Class A pan. The pan is circular, 122 centimeters in diameter and 25.4 centimeters deep, made of galvanized iron. The pan is mounted on a wooden platform with its bottom 15 centimeters above ground level. The basic pan evaporation formula is the following. In which PET is the potential evapotranspiration, E sub P is the pan evaporation, and K sub P is a pan coefficient, varying between 0.35 and 0.85, depending on pan exposure, relative humidity, and wind speed.